Well, thank you very much for having me. I'm delighted to be here, and thank you. It's just kind of a warm welcome, and you're really doing some amazing stuff here, so I'm super impressed. My name is Teachey. I'm a graduate student at Columbia University, and tonight I'm going to tell you about, sorry, got a cookie in my mouth. I'm going to tell you about work that I do looking for these things called exomoons. So you may have heard of exoplanets, and those are planets in other star systems inside our Milky Way galaxy, but outside of the solar system, right? And so far, astronomers have discovered something like 4,000 or 5,000 exoplanets in the Milky Way galaxy. And so exomoons, as you might have guessed, are moons around those exoplanets. And this is what I work on. I call them Kepler's hidden gems. Kepler because that's the name of the space telescope that we use to look for these things. The Kepler space telescope was a phenomenal mission, and I'll tell you a bit about that. I call them hidden gems. Hidden because, spoiler alert, we haven't found any of these things yet. And when I say we, it's not just me and my collaborators. No one on Earth so far has found one of these exomoons. But we're out on the trail. We're working diligently, and hope to be the first ones to do it, but whoever does it, I think it'll be in the next few years, and it's a very exciting time for me to do this work. And hidden gems because, well, if you look at the moons in our solar system, and we have quite a few of them, they're really remarkable worlds. They're exotic, they're diverse, we have an incredible amount still to learn about them, and I'd say there's every reason to think that exomoons are going to be just as exotic, just as interesting as the moons in our solar system, and totally worth finding. I always liked starting with this image. You may recognize this. This was taken by the Cassini spacecraft. Spent over a decade in orbit around Saturn. Just returned a treasure trove of images from the vicinity of Saturn. And I like this photo because it just shows the tremendous diversity of moons in a single glance, right? That big blob back in the background, that's Saturn's largest moon. That's called Titan. And Titan has a hazy atmosphere, and it's raining hydrocarbons like methane and ethane, raining down and collecting in pools, lakes and rivers on the surface. It's the only place outside of the Earth in our solar system that we know of that has a stable liquid on the surface. It's really a remarkable place. Foreground to that is another very interesting moon, very bright moon, in fact the brightest and most reflective object in the solar system. That's called Enceladus. We've recently observed geysers of water spewing off the surface of Enceladus hundreds of kilometers into space. And then there's a little moon over here, that's called Pandora. Not like Avatar, this is a real moon called Pandora. Tiny little moon right there. And then you have Saturn's rings themselves, right, comprised of billions of icy moonlets. And then there's actually another little moon right here. You might have missed that one. We call it a shepherd moon because it's got very little gravitational pull, but it's enough to kind of pull around the icy particles in Saturn's ring. So I think that's a remarkable image, and Cassini just gave us so many incredible images like that. So why do we care about all this stuff? I think that's an important place to start when we're talking about doing the work that we do in science in general, but particularly in astronomy, right? Because we're not, developing vaccines. We're not curing cancer or something like that. Astronomical research is a little more difficult to justify, at least as far as some people are concerned. So I think it's always very important to have a sense of what our objective is, why we're actually interested in doing this work, and in some cases spending a lot of money to do the things that we do. And I think with astronomy in general, but particularly exoplanets and by extension exomoons, the justification is quite profound. We're really in search of who we are and where we come from. And that's about as deep as you can get, I think. And these are questions that have been handled for thousands of years in all the cultures around the world, all the major religions of the world, mythologies, everywhere on the planet, people have been preoccupied with answering these questions. And astronomy really in the last few centuries, since the time of Galileo, the development of the telescope, we're really starting to answer some of these profound questions, particularly in the last 100 years, staring back to the beginning of time, all the way across the universe, looking at the cosmic microwave background, right? We're looking at the Big Bang. And with exoplanets and exomoons, we're interested in how not just how these other star systems form, but by extension, how our own solar system forms, right? Every time we look out, we learn something new about ourselves. And I always like to show this image too. Astronomers really went nuts about this photograph when it came out just a few years ago from the ALMA telescope. This is a microwave interferometer. It's like a radio telescope down in Chile. And this is called Protoplanetary Disk. This is a solar system in the process of formation, right? So this is a disk of gas and dust. And as far as we can tell, what we think is going on here is that planets are forming in those little dark rings, right? So this is all gas and dust, and then in those dark rings, that's planets that are sort of sucking up material and clearing out these regions in the disk. And we had never seen anything like this. This just came out 3 or 4 years ago, and it was really a remarkable image. So we're in search of who we are and where we come from. And the other thing I would say is that the universe is really our environment, and it doesn't feel that way. You know, we look up at the night sky. People in this room are very interested in astronomy, but even still, it feels very remote. It's up there, it's not down here. It's far away, it's static, it's not doing anything. And I think that's really a misconception. It really is our environment. It's, like it or not, we are immersed in the universe. And just as we're interested in understanding everything we know about the forests, about the weather, about the oceans, about the climate, I would argue that we really ought to know everything that we can about the universe, because it's not static. It's really a dynamic and it's a perilous place, and I would argue that we ignore it to our own danger. So how do we look for exoplanets? Of course, I'm here to talk about exomoons, but I think it's important to first start off by talking about how we look for exoplanets, because there's definitely some overlap in the ways that we go about looking for moons. As you might imagine, we look for planets, they look for moons. Seems like they ought to be natural, go along the same way. And there definitely is a lot of overlap, but there are also some key differences in how we go about these. So I first want to talk a bit about looking for exoplanets. So the first thing you probably think about is just, let's take a picture. Let's just point the telescope at this object and let's take a picture. And that's called direct imaging. Now if you search for pictures of exoplanets on Google, you'll probably come up with something like this. And a student of mine was doing a report on an exoplanet, and she said, well, this is a lovely exoplanet because it has oceans and it has clouds and mountains and trees. And I said, well, how do we know all of that? And she said, well, you can just see it right there. It's all in the picture. And she really thought this was a photograph that we had taken. I really would love to be able to take a photograph like this. This is an artistic rendering. And they're really photorealistic, so basically indistinguishable from a real photograph these days. And there's a lot of these floating around. Every few days, space.com has a new one of these, seems like. But this is really not what direct imaging looks like. This is really what direct imaging looks like. And these images are a few years old, but this is basically the state of the art. So what's going on here? Well, the star is there in the center. And what you can see is that they've blocked out the light from the star. And they have to do that because the star is 10 billion times brighter than that little planet that we're looking for. So it's totally lost in the glare of the star. And only when you subtract out the light through usually what's called a coronagraph, they can block out the light, and only then can they see this planet. And so they see a lot of times all this real speckly sort of stuff. This is the best they can do, and all of these speckles look like planets. So they have to do a lot of, it's very difficult work actually to try to identify planets this way, and they're getting really good, and it's getting better all the time. But as you can see, this is really, this is a far cry from what you saw in the previous image, and this is about the best that we can do as far as direct imaging is concerned. The next very popular technique is called the radial velocity method. This is a really sort of clever technique, and what it has to do with is the wobble of the star as the planet goes around. So you probably know that the star is pulling on the planet gravitationally. The planet goes around because the star is pulling on it. What you may not know is that the planet is also pulling on the star, right? So as the planet goes around, the star is actually wobbling a little bit in space. Now we can't actually see that movement on the sky, but what we can see is it's going back and forth, and what that does is, as it's coming towards us, the light from that star, the wavelength gets a little bit shorter. The light is compressed a little bit like that, And when that happens, we say that the light is blue shifted. It gets a little bluer to our eyes. Conversely, as the star is going away from us, the light waves get stretched out just a little bit, and that light appears redder to us, and so that's called red shifted. And so we can measure this to astonishing precision, and it's been utilized to great acclaim for a number of discoveries, most recently Proxima Centauri b, which you may have heard about in the news in the last year or two. This is a small rocky planet around our nearest star. It's 4.3 light years away or so. It's a small, what's called a red dwarf. So this is our nearest neighbor, and we recently discovered this rocky planet through the radial velocity method, and this is what the data looks like. So we take a lot of different observations, and this is over the course of many orbits of the planet. You can sort of fold it together in time so that you see sort of a single period, but it's lots of periods kind of folded on top of each other. And what you see is this nice sort of sine wave pattern, and that's what they're looking for. This is the telltale sign. You see on this y-axis here, this is the radial velocity in meters per second, right? So the amplitude of this signal is something like 2 meters per second. Now, how fast is that? This is basically 2 meters per second. And this is what we're seeing this star do 4 light years away or so. It's really phenomenal that we can make that measurement, but we can, and it's getting better all the time. And we're looking at a star walking away from us, basically, 4 light years away. And finally, you may have heard of this thing. Oh, this video's doing something kind of funny. The transit method. So what you're looking at here is the transit of Venus. Venus transited the face of the sun most recently in 2012, and I hope you saw it because the next one's not until 2117. This happens very rarely, and this has to do with the geometry of Earth's orbit with respect to Venus's orbit. Now we can use the same principle. You see what happens here is that Venus is passing in front of the star from our point of view, and so it's blocking out just a little bit of the sun's light as it does that. And you can use the same principle to look for exoplanets, because you look at a star far away, and if that planet happens to pass in front of the star from our point of view, and the geometry has to be just right, then you can see a little dip in the intensity of starlight. And the good news is when we're looking at exoplanets, this happens like clockwork. If it comes around once, it'll come around again and again and again. Venus is, this is because we're immersed in the solar system that this is a very rare event. But transits of exoplanets happen quite regularly. And this is what it looks like, right? So if we're monitoring the brightness of the star over time, here's the brightness of the star, and then as the planet passes in front of the star from our point of view, there's just this little dip. It looks kind of like a rounded out trapezoid. That's the telltale sign of a planet, and then as the planet exits, then the starlight goes back to what it was doing before. And this is actually the very first transit that was ever observed. This is just in the year 2000. This fellow, Dave Charbonneau, was a graduate student at the time, and now he's a professor at Harvard, so he's doing pretty well for himself. And his professor, they had already discovered a planet in this star system through radial velocities, I believe. And so his professor said, we already know there's a planet there, and I think there's a good chance that it's going to transit. So go out and look for it. And so he set up a telescope literally in a parking lot to look for this, and he got this data, and it was a big splash at the time. And this is just the year 2000, right? So less than 2 decades ago, and we hadn't seen a single one of these. But it really is exploding now, thanks in large part to the Kepler Space Telescope. So this is a telescope up in space. It's still, of course, it's not coming down at all. But its primary mission has now ended. The primary mission, it spent 4.5 years staring at this one patch of sky. This is Cygnus. Here's the Milky Way, of course, and that's its footprint on the sky. There's a bunch of CCDs, right? This is just a camera on the sky, and it stays there, and it's incredibly stable. So it spent 4.5 years staring at that one patch of sky, monitoring 200,000 stars and taking photographs again and again and again, and just made a movie of this sky, basically. We got data on some 200,000 stars to look for these planetary transits. You have to monitor a lot, because you can think about it, they have to be lined up, right? The geometry has to be just right. So If they're tipped a little that way or a little that way, you won't see it. So you can imagine that most stars, if they have planets, we probably won't see the transits of those planets. There's only a small fraction of the planets for which the geometry is just right. So you have to look for a lot of stars in order to see these. But it's been tremendously successful. Plot is a little bit out of date, but these are all the exoplanet discoveries made through a variety of different techniques, color-coded by the technique that was used to find them. And you see that transits are just running away with it. They've really been the most successful, largely because they're quite easy to do, comparatively easy to do. Now, Kepler is not the only name in the game. You might have recently heard of the TRAPPIST-1 system. This one really made a big splash because it was 7 planets, and it was such a big splash that it got its own Google Doodle. But these were 7 small planets, rocky planets. There's 1, 2, 3, 4, 5, 6, and the 7th one. And you know, this was really exciting because they're all packed very close together. And rocky planets, you know, the big gassy planets are very easy to find. Rocky planets much more difficult to find. And so to find 7 of them like this, a few of them, 2 or 3 of them, considered maybe in the habitable zone. This is the region of space where it's just right temperature. You're not too close to the star. You're not too far away from the star, so you can have liquid water, perhaps. And so this was very exciting. And this is what the data looked like. So here are the transits, right? Remember these rounded trapezoids? And so here's the innermost planet, and here's the outermost planet, and these are all the different planets here. And you wanted the duration, right? You see this is time on the x-axis. So these durations are changing. And that's because the inner planet is orbiting very quickly, right? The farther out you go, the planets move slower and slower, right? So the same planet, if it's much farther away from the star, it will take longer to pass in front of the star from our point of view, and so the duration of these events go from very short to significantly longer. And this was one chance event where they had 3 planets transiting all at the same time, and so you can get these really goofy kind of looking transits. So it's pretty exciting. But why exomoons? So I've spent all this time talking about exoplanets, but I'm of course really here to talk about exomoons. Why are we interested in these things? Well, the first thing that I would say is that we are interested in the formation of not just these moons, but of the systems that host these moons. And by extension, as I said before, when we learn things about other systems, we're really learning something about our own solar system as well. Why did I say that? Well, if we look at our own solar system, we see lots of moons, particularly in the outer reaches of the solar system. Around Jupiter, around Saturn, around Uranus, they have a bunch of moons. And so you'd say, okay, well, it's just a reason that they're here. They ought to be elsewhere, right? So it's probably not a fool's errand to be looking for these things because we feel pretty confident that they must be out there because we see them here. But what if they're not? You know, this is an important thing to remember. You know, our preconceptions are often wrong, particularly when we are thinking about things going on in space. We're constantly surprised. We learned about these things called hot Jupiters. These are planets that are the size of Jupiter that orbit their star once every 8 hours or something like that. They're so close to their star. Nobody anticipated that whatsoever. And so we continue to be surprised. All the time there are discoveries that surprise people or are unexpected. And so if we didn't find moons out there, that would sort of be surprising, but that would be a very important piece of information, because when we're thinking about how life arose in our solar system, you know, how did things come about, and is it a very special set of circumstances that led us to being here, or are the same things that were going on in our solar system happening in 100 billion other places across the Milky Way galaxy? This is an important question to answer, and moons would tell you one little piece of the puzzle, because if we didn't find them out there, then that would be puzzling, but that would be very important information, say, at least in this regard, our solar system might be somewhat unusual. And so we think that the moons around Jupiter, Saturn, and Uranus probably formed something like this. So you have a disk of material. Remember that protoplanetary disk that I showed you earlier? You have a disk of material, and the planets sort of are grown out of that disk of material. And we have strong reason to believe, because Jupiter and Saturn, they look sort of like mini solar systems in their own right, that the moons are forming out of another disk of material around those planets in the early days. So we think that there's this disk, and then the planets have their own disk of material, and the moons are coming out of that. Now that's not the only way to form a moon, of course. Another way to form moons are through impacts, like this one. This is how we think that Earth's moon was formed, to the best of our knowledge. There's still some debate about this, but the most accepted explanation for our moon, which is quite large with respect to the Earth, is that a giant impact, an object about the size of Mars, very early on in the solar system's formation, slammed into the Earth, blew off all of this material, and this material starts swirling around and eventually coalesces to form our moon. Now, I mentioned, they can form out of a disk, they can form through impacts, and then there's one other widely accepted way of getting a moon, and that's through capture, right? So Neptune has a large moon called Triton, and as far as we can tell, we think that that moon was captured from what's known as the Kuiper Belt. This is where Pluto resides. So Pluto is a Kuiper Belt object, and as far as we can tell, Neptune's largest moon was also a Kuiper Belt object that was captured by Neptune's gravity and then became a moon of Neptune. The reason we think that is because it's going in the wrong direction. Basically, everything in the solar system goes counterclockwise, so this thing is going clockwise. And there's a few cases like that, and those are sort of unusual cases. Okay, so moons can tell us about formation. Why else are we interested in moons? Well, moons are major worlds in their own right, at least as far as our solar system moons are concerned. So these are the major rocky and icy worlds of our solar system, ranked in order of size. There's the Earth, of course, and then Earth's evil twin, Venus, basically the same size. Mars is about half the radius of the Earth, only about a tenth of its mass, I believe. So that's sort of crazy. And then next you probably think, okay, well, Mercury, right? Well, it's not Mercury. Ganymede, the largest moon of Jupiter, is next down the line. And then after that, the largest moon of Saturn, Titan. Right? And then we get to Mercury, right? And then we have more moons: Callisto, Io, Earth's moon, Europa, Triton, and then that ne'er-do-well dwarf planet Pluto. And so it's easy to say, of course, a lot of people think that Pluto should be called a proper planet instead of a dwarf planet. I won't get into that discussion, but it's easy enough to see that these moons, if they were orbiting the sun directly, rather than orbiting a planet, sort of orbiting the sun indirectly, then we would definitely call these moons planets in their own regard. And look how diverse they are. Every single one of them is astonishingly different from every other one. And they're just as interesting. And so, moons in our solar system are remarkable places that really deserve exploration. And again, I would say that exomoons are going to be just as interesting, just as diverse. I think we have this tendency to think of things out there, exoplanets and the like, as sort of one class and they all look the same. We call these things hot Jupiters. Well, everything must look like Jupiter, right? Well, probably not. There's probably a wide diversity of these things. But at this point, it's anybody's guess. What else? Moons can have lots of water. I'm talking lots of water. I love this image. This is the Earth, of course, stripped of all its water and put into that blue sphere there. That represents all of the water on the Earth. Next to it is Jupiter's moon, Europa. Now, it's a much smaller world, but it has more water than the Earth. Europa, we believe, has a global ocean. There's an icy shell that's maybe 10 kilometers thick, and then underneath that is a global ocean. And it's anybody's guess what's in that ocean, but we have good reason to believe that it is a liquid ocean. So what is under there is a tantalizing question. And then going along with that, moons can have internal heating. This is a composite image, obviously. This is Europa again. That was photographed close up by a space probe. I don't know if this was Galileo or what. But overlaid with that is this sort of pixelated thing. That was data collected by Hubble. And what that's showing is geysers, big plumes of water shooting into space. I mentioned Enceladus has these sort of things, and Europa has these things too. That's very exciting because what it means is that we can sample the material of the water underneath. We can sample Europa's water without having to drill 10 kilometers through an icy shell. We can fly through this stuff and sample it, and that's very exciting. People are getting very excited about that. But this is internal heating. What happens here is that the planet is injecting a lot of energy through its gravitational tides. The best example I've heard before is you take a stress ball and you start squeezing it. In a very short amount of time, that stress ball is going to get quite hot because you're putting energy into that ball, and there's this internal friction. This is all coming from the gravitational pull of the planet, and it really puts a lot of energy into these moons, enough energy to blow this material hundreds of kilometers into space. And so if we have internal heating, then we might have something like black smokers. This is footage from the bottom of one of Earth's oceans, and before anyone went down there, everybody thought this would just be this barren, desert deep underwater. It's incredibly cold. It's incredibly deep. There's no sunlight. Pressures are extraordinarily high. And then they found these black smokers, and they were oases on the bottom of the ocean. Just whole ecosystems thriving down deep, just eating the chemicals and not needing any sunlight at all. And so if you have these things on the Earth, first of all, we don't really know how they got there. But life is thriving under the most extreme conditions. And so you have this internal heating mechanism. This is coming straight out of the Earth. And it stands to reason that you could easily have something like that on Europa. So put it all together, we have water, we have internal heating. Of course, I'm getting around to life, right? Life is really what it's all about, I would say. So we're talking about formation, we talk about these moons, very, very interesting geologically. But for me, anyway, the search for exoplanets and the search for exomoons is really driven a great deal by the search for life. And there's one more important thing that I want to say about life with regard to these exomoons. And this is this thing called biosignatures. So, what you've probably heard when we're looking for extraterrestrial life, people are listening for radio signals, say, something like that. But that's not the only way to look for life. You can also look for life by looking for signatures of life in the atmospheres of exoplanets. So if an extraterrestrial astronomer were looking at the Earth, they might very well deduce the presence of life on Earth because we have a lot of oxygen and a lot of methane, all living comfortably together. Now, I'm not a chemist, but the chemists tell us that oxygen and methane really do not like to live together. And the reason that we see both of these in such abundance in the atmosphere is directly tied to the fact that we have a thriving ecosystem here, tons and tons of life on the Earth, and that is responsible for putting this chemical signature in the atmosphere that really would lead someone to believe that life is there. So here's the problem. Say you're looking at a planet and that planet has a moon. Well, what if the planet has a bunch of oxygen and the moon has a bunch of methane, right? We remember Titan? Titan has a bunch of methane. That whole atmosphere, it's raining methane on the surface. Of course, we have a lot of oxygen on the Earth, but you could have a lot of oxygen without it being generated by life. So you have the planet has a lot of oxygen, you have the moon with a lot of methane. You might say, okay, well, I found a biosignature there because they're living together and they really shouldn't be. But you'd be wrong, right? That'd be a false positive because what you're really seeing is two different objects, and you're getting them confused. So I highlight this point because we're really going to have to solve this problem, and so far no one has solved this problem of how to disentangle these two signatures. But I would argue that you're really going to want to know for sure that you've got a moon or not around a planet if you're ever going to claim the existence of life based on something like this. So there are major hurdles for detecting exomoons, as you might have imagined, because we haven't found any yet. It's sort of difficult to do. It's difficult work. So the first thing you probably could say is, can we take a picture? Direct imaging. What about that? Can we take a direct image? Well, not really. Not yet, anyway. This is just a little bit out of reach, at least today. Now, in 10 years, 20 years, we might be doing much better, but this is about the best we can do. That is a very large planet. It's a gas giant. It's about as far away from that star as Saturn is from our sun, about 10 astronomical units, very, very far away. That planet's also quite hot, makes it easier to see. And the separation between the star and the planet is 1/10,000th of a degree. For anyone in the room who's not used to thinking in terms of degrees, if you take the sky, you can break it up into a semicircle, right? Because half of the circle is below us and the other half is above us. So from one horizon to the next, that's 180 degrees, right? So 180 degrees from horizon to horizon. Now imagine how large 1 degree is. It's pretty small. Imagine 1/10,000th of a degree. This is very, very small, but we're able to resolve that separation. What about a moon around that planet? Well, that separation would be 1/10,000,000th of a degree. And you can see that this is state of the art, and we're just not going to be able to see it, right? So that's we're out of luck as far as direct imaging is concerned, at least in the short term. We've got to have better technology in order to try doing it that way. What about radial velocities? Remember, this is the planet tugging on the star. Could we see it that way? So remember, when we're looking at radial velocity, we're just looking at the star. We can't see the planet directly. We can only infer its presence. Well, here's the problem. Here's the star, and here's the planet and the moon going around, and they orbit a common center of mass. Well, it's that common center of mass that's really pulling on the star. And so whether or not you've got a planet there, or just a planet, or a planet and a moon, you're really not going to see that signature at all. So we're back to transits, right? Transit's been the most successful way of looking for exoplanets, and this is sort of our best shot, at least right now, for looking for exomoons. Now I want to stress that this is simulated data. This is not real data. If we had seen something like this, we'd be very excited. But this is what you might see if you saw a planet with a moon. So there's going to be a big dip because the planet is passing in front of the star, and then there's going to be a smaller dip because the moon is passing in front of the star. Now this gets tricky because if you think about what's going on here, the planet is going around the star and the moon is going around the planet. Well, the planet is going to transit more or less like clockwork, right? It comes around again and again and again. But that moon is going to show up in a different place every single time that planet transits, right? So sometimes it's going to precede the planetary transit, sometimes it's going to come after, sometimes they happen at the same time, and so that can be really weird. And really what we do a lot of times when we take these observations is that we'll take many of these transit events and we'll stack them on top of each other, and that makes the signal much easier to see. But these moons, they're showing up in all different places, so they just don't stack that same way, and they don't really work out terribly well. And you can see that the size of these signals, these are data points, and this is, you know, error bars, right? You can see that the data is not clean. It's really noisy, we would say. And so these moon signals can really just be lost in the noise. If I took away these lines, it just wouldn't look nearly as clear to you. You can see the lines, oh yeah, there's a little dip, there's a little dip. But take away the lines, and I would challenge you to see the moons in some of these things, because they're really quite noisy. So we have to get a little more clever about how we do it. We still look for those moon transits, but we can do one better than that, and look for these things called transit timing variations, as well as transit duration variations. What's going on here? Well, you have this moon going around the planet, and the planet's going around the star. The moon is tugging on the planet, just as the star is tugging on the planet, and the planet is tugging on the star, all of these little wobbly sorts of things. So you can imagine that if the planet didn't have a moon, it would go around like clockwork, right? But with the moon there, all of a sudden the planet is sort of wobbling around. So what that means is sometimes the transit comes early, and sometimes it comes late. And you see enough of these events and it will sort of make this pattern that you would say, okay, that has to be a moon. So the timing of these events can shift, as well as the duration of these events can shift, because again, the planet no longer has a single velocity as it passes in front of the star. It slows down and it speeds up and it does all kinds of kooky things. And so the duration of these events can change as well. So we're looking for these things indirectly by the gravitational influence of the moon. So that's pretty cool. So we put it all together. We look for transit timing durations. We look for duration variations, as well as these dips. And that has really been the way most people have looked for moons. But we do have some new results. It's not all is lost. This plot is not showing up for some reason, but this is our well, this is a black screen, but our recent work, what we did was we took many different planets and stacked them on top of each other. I mentioned before how we look for planets just stacking things on top of each other. Turns out that we can, and I'm glossing over all of the gory details that you're not interested in, but it turns out that we can take many different planets and stack them on top of each other and look for the moon signal. So what we're looking for is there's this main dip from the planet, and then these moons produce all different dips. They might be in all different places, but if you stack enough of these events on top of each other, you would expect to see just a little bit of starlight that has been removed by the cumulative effect of these moons being present around these planets. So we did this work, and our results indicated that moons appear to be exceptionally rare in the inner regions of these star systems. Now, I want to be clear about this, because I said before, if we don't find these moons, that really tells us something special about our solar system, maybe. So we see a lot of moons here, we don't see a lot of moons elsewhere. Is that telling us that something is special? Well, I have to caution you against drawing that conclusion, because what Kepler was able to see was really just stuff very close to its star, right? If you think about, we only have four years to look at these things. So the planets that are whipping around their star, we can see them again and again and again and again. But the planets farther away from their star, they orbit much, much more slowly. And so there's a good chance that we didn't see any of those planets at all. For example, Jupiter takes 12 years to orbit, right? We had 4.5 years of observing with the primary mission of Kepler. And so you basically have a 1 in 3 chance of catching a transit of Jupiter, right? There's a good chance that it transits all right, but not in the window where you're looking, right? So these distant planets, whereas we have good reason to think the moons could be there, because that's where we see them in our own solar system, we just weren't able to see those with Kepler. We couldn't see very many of them, right? So the moons appear to be rare in the inner regions of the star system. Now, that's consistent with what we see in our solar system, and it also corroborates recent theoretical work, which also suggests that these moons might be lost as planets migrate to the inner regions of their solar systems. But I do have one more thing to tell you about, and that is that we do have a single exomoon candidate called Kepler 1625b. Someone on Wikipedia helpfully generated this image for us. This is what our modeling suggested this system might actually look like. That the planet is about the size of Jupiter, but our numbers indicate it's maybe 10 times as massive as Jupiter. It turns out that you can pack a lot more mass on these objects, and they don't get any bigger. They actually get smaller as you add more mass to them. And the moon, if it's real, appeared to be about the size of Neptune. Now, that is reason enough to be very skeptical of this thing pending additional observations. No one has expected to see a moon like Neptune, right? I told you before about how we're always seeing unexpected things. However, we don't expect to see unexpected things. We expect to see ordinary things that we expect. And so a moon the size of Neptune, no one has expected that. And so we identified this thing, and we asked for time on the Hubble Space Telescope to observe it. A journalist from a publication that will go nameless found out about this and said they wanted to write an article about it. And we said, well, please don't, because at this point it's a candidate. It's not a confirmed discovery. And we don't want to get people excited about something that doesn't exist. Right? So why am I telling you about it at all? Well, we had no choice, really. They decided to write this article, and sure enough, this thing really literally went around the world. There's a Turkish and Estonian and Polish and just all over the world. It was really sort of remarkable to see this coverage around the world. Even though we didn't want it, some people say that any publicity is good publicity, but anyway, that was the hand we were dealt, and we played it. But this was the data that we actually saw in Kepler. So 3 transits, and this was taken from our paper. Someone helpfully drew the geometry of the system so that you could kind of understand what's going on. But this is what we expect to see. We see a dip from the moon, and then here's of course the dip from the planet, and then this, that would be the signal from the moon. But you see it's very noisy, right? So this dip, again, the line is really doing you a favor by sort of connecting the dots for you, but that's what it looks like, and that's what we expect to see. And that was good enough. We tried to rule out the moon hypothesis, but the moon hypothesis remained the favored hypothesis. And so we made the Hubble observation on October 28th and 29th. That was 40 hours of observing time on Hubble. I started on a Saturday morning and went through Sunday night, and it was incredibly nerve-wracking. I gave it all the commands, and there's no joystick or anything. I gave it commands months ahead of time, and then I didn't sweat it at all until after it was over, and then I was convinced that we had done something wrong. But I don't think we did something wrong. In fact, I'm pretty sure we did it right. So this is what we see from Hubble. This is our target star, and we only have a single image that looks like this, and then we have 250 some images that look like that. You might be wondering what's going on there. We use what's called a grism, and so what that does is that it spreads the light out from the star like a prism, right? Spreads the light out across the camera. So this star is spread out over there, that one over there, and that one right over there. Spreads the light across the star, and what that does is that you can make measurement at different wavelengths of light, right? And what that allows us to try to do is characterize the atmosphere of this planet. So we really wanted, you can do this for free. It made analyzing the data a bit more difficult to do. But it was worth it, I think, because we're working on characterizing the atmosphere of this planet, which is pretty exciting. By the way, no one has tried to study an atmosphere of a planet so far away from its star. People have done these studies for hot Jupiter's planets very close to their star. This star has an orbital period of about 287 days, right? It's about 9.9 astronomical units, about 90% the distance of Earth from the sun. So no one's tried to do that, but that was pretty exciting. And this is what the raw light curve looks like. Now let me caution you against trying to read anything into the little bumps and wiggles here. This looks terrible, frankly. What's going on here is that the camera has these things called electron traps. And so the light comes in and it produces these electrons, but they get trapped, and so it's sort of, I've likened it to water coming into a rowboat, and you're bailing out the rowboat, but the rates of these two things are, more water is coming in than you have time to bail out. And so it makes these incredible ramps in the data. And those were very difficult to deal with. We finally got a handle on them. And so we had to cancel out all of these systematic effects in the data. So I'm not showing you the cleaned up version because our paper has not yet come out. But this is really what it looked like when we extracted the light curve, and this was quite challenging. We had expected to see something like this, but the degree to which we see this thing has been quite challenging. So we spent quite a bit of time analyzing the data, and then in the meantime we've also gone back and been analyzing the Kepler data in more detail. We're working diligently to get these papers out to really characterize this thing, tell you whether or not there's a moon. This is really some of my most recent work here, simulating and understanding what Kepler is actually seeing. So this is what Kepler sees. These are all what we call point sources. It's just a point of light, but the camera makes them sort of appear a bit blurry. So this is what the camera would actually see, except that it has these giant pixels, right? So this is a simulation, but this is really what Kepler would look like. And so you can see that there's a lot of overlap. These are the pixels that they extract to make the Kepler light curve. And all of these stars, they contribute different amounts of light to these pixels. And it turns out that the catalog for which Kepler was using to generate their own simulations of these things had a star that, as far as we can tell, doesn't even exist. And they had placed it right there. They said the star existed right there, and it does not exist right there. And so all of their numbers are wrong, and so we've been going back and trying to get a better handle on those things. So that's just a little flavor of a day in the life of an astronomer. A few days working on this. So stay tuned. We've got proprietary access. Means the data is hours and hours alone until end of April, at which point anybody can get their hands dirty. We've had a heck of a time analyzing this, so if you want to jump in on it and write a paper in a single day, have at it, but that I think you might have some difficulty. But we're trying to get all of our stuff, analysis done by end of April, and we'll have an answer. Let me briefly say that regardless of what happens here, I think it's a very exciting time. Of course, we would like to find this exomoon, but if we don't find definitive evidence, I think this is still very exciting, because this means that the truly first unambiguous detection of an exomoon is still out there. It's still waiting to be found. And some people have written articles saying we're hanging all our careers on this one discovery. I'm just a graduate student, so my career is going to be quite short at that. But you know, it's not the case. Exoplanet science has just exploded in the last 2 decades, and we've found thousands of these exoplanets. We haven't found a single one of these exomoons, and so they got to be out there. And whether or not this one is the one, it remains to be seen, but I think regardless of what happens, it's really an exciting time to be getting into this field. And so before I finish, let me say, if you haven't checked out this website, this really got me into the work that I do. planethunters.org, and anybody in this room can get on and set up an account, and you can start looking for exoplanets. This is real data taken from Kepler, and you can get on there and analyze it, and they tell you what you're looking for. You're looking for these little dips, right? And so you say you've heard my talk, and now you know what you're looking for, and you don't have to even read the instructions. So you can get on here and look for these things, and maybe if you are responsible for helping finding an exoplanet, then your name will go on a scientific paper, and forever after you are a co-discoverer of that exoplanet. So thank you very much for your attention. I've been delighted to be here. And I'll take questions if there's time. Yes.
So when you look for exomoons, I assume you look much closer than exoplanets.
It's a great question. Ideally, yeah, that would be great. The closer the star is, as you might imagine, it's going to be brighter. When you have a brighter star, your what we call signal-to-noise ratio is going to be a lot better. So we'd like a star to be as close as possible. Our candidate, Kepler 1625, is about 4,000 light years away. That's not great. That's a little far. That's much farther than we'd like it to be, honestly. And so our signal-to-noise is much lower than we'd like. So you know, a lot of adversity, you know, things working against us in terms of making this.
What about the stars that are very close, like 4 to 15 or 20 light years away, rather than 4,000? Does that help you or not?
Well, yeah, that'd be great. As far as I know, that nobody has seen anything real clear from those planets. Again, you know, I think we're zeroing in on an answer that is, these moons are not to be expected very close to their stars. And so Proxima Centauri B that I showed you before, that was, of course, that planet actually doesn't transit. That's only a radial velocity detection. But planets like that would be attractive targets, but I think what we're coming around to, like I say, is that those planets are unlikely to have moons. You know, Mercury has no moons, Venus has no moons. So it seems increasingly clear that we have to look at greater distances from the star. Yes?
I understand that the methods used to detect it would be used or still, if they do in fact prove to be successful, they still work. But isn't Kepler 1625b really straddling the borderline between a brown dwarf and a planet at 10 Jupiter masses?
That's a great
question. We now know that the brown dwarf line probably falls somewhere around maybe less, possibly a little less than 10.
Yeah, that's a great point. Yes, this is a recent result that you're referring to that says that so a brown dwarf is what people typically call a failed star, right? So it's a big ball of hydrogen and helium, same kind of stuff that the sun and all the other stars are made out of, but it wasn't massive enough to start hydrogen fusion. My take on this is that it's a bit of a semantics argument.
It's still the same method used to discover the moon or planet.
It's exactly, that's
So
right, yeah.
If it does turn out to work, you've still proven your method works.
Exactly right. But you know,
doesn't
what is the
make
dividing
sense.
line between a planet like Jupiter and a brown dwarf? We're putting a mass on that, and we're really getting into the weeds here, but this has primarily to do with how they formed, whether or not they formed in that disk of material surrounding a star, or whether they formed kind of like a star out of direct collapse out of a molecular cloud or something like that. So it's a great point. I think our stance has been to just do the science and let other people worry about the terminology.
Yeah, I just thought what you thought about that.
That's a great question. Yes.
You mentioned that you can have a planet without a moon.
Mm-hmm.
Can you have a moon without a planet?
Well, that's a great question. I would say that the moon is sort of defined by its proximity to its planet, right? So we're talking about a satellite, so you know it has to
So
be
you have to have
going
place to
around,
go.
right?
Okay.
So is a planet if it's not going around a star? Well, yeah. People have said that there's these things called rogue planets that were born as a planet and then they're ejected off into space and then just flying through, you know, the darkness for eons on end. But yeah, the short answer is, you know, maybe you might say it was born as a moon and then it was ejected and then it's a rogue moon or something
But
like
yeah,
that. For
not
practical
really.
purposes, it ought to be around a planet. Yeah.
Okay, thank you.
Yes.
Your candidate exomoon,
Yes.
I have an idea what the orbit is. Is the barycenter inside the planet?
The berries, yeah, I think it is.
Ah.
Yeah, it's a great question. Yeah, so that was another question that people came up with. You know, why aren't we calling this a binary planet? You know, so if the planet is the size of Jupiter and the moon is the size of Neptune, that looks like two massive planets. Why not just call them a binary planet?
The mass fraction of the mass of Neptune compared to the 10 times mass of Jupiter is something like 1 to 100 still. So you're looking.
Yeah, it's about.
So it is
right.
well within the mass that defines the moon.
Exactly right. Yeah. So that's again getting a little bit into the weeds, but the ratio of the masses between the two objects is going to determine where that center of gravity is. Right. In the extreme where you had two planets that were exactly the same mass, that center of gravity would be directly between them. But once you have one that's much more massive than the other, then the center of gravity moves until eventually the center of gravity is inside the planet. So Earth and our moon, the center of gravity is inside the Earth, but it's not right dead in the center. So Earth actually orbits the center of mass. It sort of orbits this little space inside the Earth like that. Pluto and its largest moon, Charon, on the other hand, has the center of mass, what we call the barycenter, is outside. So they, you know, a lot of people will call that a binary system because they're really sort of orbiting each other rather than one going more or less around the primary. Great question. Yes.
Does that ratio that you were mentioning affect whether the moon is eventually going to be drawn closer in or escape the planet that is, like our moon is eventually going to leave us? Does that center of gravity move as that happens?
I haven't done that calculation. Yeah, I would assume it moves. It's capable of moving, but yeah. So what we tend to be concerned with is sort of the dynamical lifetime of these systems. You know, so what can they survive a billion years or something like that? And yeah, we're pretty comfortable on that one. Yeah.
With the transit method, has there any been clear information as to determining the tilt of the orbits in terms of an entire system as well as individuals?
The tilt of an entire system? What do you mean by that?
In other words, I mean, is there something analogous to the ecliptic, where pretty much they're all in the same plane closely?
Sure. Yes, that's so we definitely have seen systems that are way off that sort of thing. You know, so the ecliptic. You know, this is this plane of our solar system. It's more or less the plane that all of the planets lie in. Of course, there are some differences, right? We have inclination differences between all of our planets, and that's why we don't see Venus transit all the time, for example, right? We're tilted with respect to each other, so sometimes we line up just right, most of the time we don't line up just right to see Venus transit. Yeah, so, in the case of TRAPPIST, for example, TRAPPIST-1, all of those are clearly more or less on the line, but they do have some sort of, let me see if I can get back to it real quick. Not far. Okay, yeah, this is the one. Yeah, so they're transiting. Those are pretty close to one another, and that is certainly expected. But like I say, we definitely have observed examples where things are really off kilter.
So you showed a graph that showed the transits are proving, show the most, are the most obvious way now to find them, because so many are off of that. So how frustrating is it to know that you're looking for that needle in a haystack in a very small haystack, or a very large haystack?
By virtue of the fact that most of them do not
Most of them you'll
transit.
never know.
Yeah,
see.
it's yeah. I'd certainly like to be able to see more of them that way.
Yeah.
No doubt about that. We can extrapolate a lot from statistics, right? So we know, this is just a geometric probability, how far away a planet is and how likely we are to see it, right? And so build up enough statistics. At this point, we've seen thousands of planets. There's good reason to think that there's probably 1 trillion planets in the Milky Way galaxy. We will only see as, if we could only see 1% or a fraction of percent, there's still a lot to be,
And is there any buzz within the community as to the next way to detect? Like,
well, that would be
is
brilliant.
there, would there be?
There's sort of stuff goes on at the margins. There's a graduate student that I work with who's kind of come up with something novel that is, without going too much into the detail, what can happen is that the planet pulls on the star in such a way that it distorts the shape of the star. The star is not perfectly round, but it gets sort of egg-shaped or something like that. And so a friend of mine is working on just that, is to see, this planet is going around, what does that do to the shape of the star, and how might we observe it? So there's definitely still, active research. Hard to imagine something being more effective than radio velocity transits. All these are now getting into real special cases where the planet has to be really close to the star and has to be really massive and those sorts of things. But yeah, this is what this is what we do, is try to figure out these sort of novel ways of skinning the cat.
All right.
Great. Excellent. Thank you very much.